Isn't that
Yeah,
nice? Very good.
yeah.
Today's experimental mathematics seminar speaker is a renowned experimental mathematician, Victor Moll, who will talk about the method of brackets, the heuristic method for integration. As usual, you're welcome to unmute yourself any minute to interrupt Victor. Otherwise, please mute yourself. Thank you.
Okay, thanks. Thanks for the invitation. Can you hear me? So
Yes,
I
we
hope you
hear you
hear me
very well.
well. Okay, good, good. So thanks again for the invitation to speak. It's always a pleasure. I wish it would be in person, but I'm avoiding traveling for the obvious reasons. The less obvious reason is that today is part of Mardi Gras, so one has to be in New Orleans. So, I'm going to tell you a story. And first of all, I have to tell you some of the collaborators in this project. And collaborators are two Chilean physicists, two former graduate students, and a current graduate student. Okay, so this is the people that now are working in this is part of the project. And let me start with a calculation. So here's a problem that you should give your students in calculus. So I want to suggest a new way to evaluate this classical integral. So the first thing you do, I'm not going to say you should do, but say the first thing you do is you expand the integrand. You take the exponential function and you write down the series. Then you exchange the integral and the sum. I was told once when I was a grad student that the only time you cannot do that is in a qualifying exam problem. So there you have the integral, and then you see that this is integral that appears here. So I'll write it again. And
I laughed at your joke, Victor. I don't know if you heard me. I was muted.
no,
but,
you were muted. Yeah. Okay.
Yeah, but I laughed.
Yeah, I also laughed.
Good. Okay, so then you have this integral, and I'm going to introduce two notations. The first notation is for this quotient that appears here, -1 to the k over k factorial, that will reappear. I'm going to call it phi k. And then this integral that appears here, the integral of 0 to infinity of x to the k, I'm going to call it the bracket of b. B is going to be the exponent. And for making the formulas look cleaner, I'm going to subtract a 1 there. So the integral becomes this object. And if you're worried about convergence issues, you should notice that this integral is divergent everywhere. I mean, at 0 and infinity, depending on k. So we have this formal object. And now there it is again. So this phi is some ratio of an exponent, an alternating sign, and a factorial. And this symbol with the bracket simply is an integral. So here's the rule. What you have to do to evaluate this integral is the following. You solve the equation k plus 1 equal to 0. K plus 1 equal to 0, I can solve. K plus 1 is the bracket appearing here. Right? So you get k star equal -1. Then you assign to the sum the following value. You look at the function appearing outside the phis and the bracket. You replace k by a k star, and then you multiply by a gamma factor. And then the integral is simply given by the sum. You get a to the -1 because k star is -1, and gamma of 1 is, and you get 1 over a. And that's it. We're done. Okay. I've been informed that I might run out of battery, so we'll see. Okay. So the general problem that I want to address is this. Okay, before I continue, I email my talk to Doron. So if Doron can email somebody who will help me along the way once my battery dies, but I apologize in advance. But
I will forward it to Robert. Okay.
Sorry? Yeah, okay. So
yeah, okay. In case.
We might have to take a, yeah, okay. So then the general problem that I want to address is you have your favorite function, and then you want to determine the integral, some properties or everything. So I want to show you how to use this method to to do Wallace's formula. So sorry, before I continue, I want to show you some examples of integrals that for the method applies. I want to give you, I know that not everybody's in love with integrals as I am. So I want to show you some examples. The first one is Wallace's formula, clearly not stated in this form because the formula is before the integral sign appeared. Then there's a nice quartic analog with a very nice polynomial appear on the right-hand side, where the coefficients are a combination of sums of binomial coefficients, so things that Doron loves, and they have lots of interesting properties. Then this quartic integral appearing here appears in a very strange series. So you take a double square root function and you expand as a function of c. And this, for some reason, this quartic integral appears in this series. So when we started looking at integrals to evaluate, when we saw this connection between quartic integrals and this double square root, I looked for integrals that have this type of functions. And the famous table of Grashet and Rizek had this beautiful formula. So you take there's a simple rational function here with a square root and then to the 1/2. So you see the double square root. That's what I was looking for. It's a beautiful formula. Unfortunately, it's incorrect. Right, and I got myself involved in the table of integrals because I kept on complaining about this formula, and now I'm stuck being the editor. So the moral of this is that one should not complain very much, but it's hard to change old habits. So I want to notice the formula is something to the 1/2, right? The correct formula is this. Somebody forgot to type a 3 in the entry. And there's a beautiful paper in the archive where some person did a lot of interesting manipulation with hypergeometric functions to figure out what the correct formula should be. The 3 there.
What's phi in this formula? If phi is any
Phi
rational?
Phi, I did not write it down. It's a simple rational function.
Any
of x
rational
squared.
function?
No, a specific one. A specific rational function of x squared. Something like 1 plus 3x squared over 5 plus 7x squared. I didn't want to copy it. Yeah. So the answer
and
to
if you don't, in the original version, do you have any answer in the original version?
For the original?
Yeah.
You should be a bit more patient, my friend.
Okay.
There's the answer. Okay.
Ah.
The answer is a difference of 2 elliptic functions. It's sort of an ugly. I decided not to show you the formulas for pi and f because they're long.
So it's
And
explicit.
the only thing that is different here, the 3 that should have been the 3 there was typed as a 1, and gave me headaches for a long time because I tried to prove this formula for a long time. I should have done a numerical check. You do a 1 numerical check and you realize the answer, the formula is not correct.
So the second formula is much nicer because it's more complicated than the first one. The first one is
Well,
trivial.
it depends on your taste. Depends on your taste. Okay, we're not going to argue about that. Okay, the other thing you can do with the integrals, there's things that, for example, you can define new functions, right? This is the origin of integration, and you can define the log. You have to make sure when you create a new function that somebody didn't do it before you. So, for example, you can combine things and you get the gamma function, and then you can combine these functions and produce more combinations of things. So, for example, we were playing at one point with log of gamma to a power, and there's a beautiful formula of Euler that says that the integral of log gamma is log of square root of 2 pi. And this is, we found this by chance, this formula for the power log gamma of q square. It's a combination of Euler's constant, pi, and the previous integral, and derivative of zeta. Okay? So it's natural that once you have 2 examples, once you have L1 and L2, then you ask for the general formula. So what's L3? And then this is, we asked this in 2002. In 2013, John Borwine, Bailey, and Crandall finally got it. And depending on whether you like it's pretty or not, this is a horrendously long formula. It involves lots of complicated things. For example, it involves these width and zeta functions and many other complicated things. I'll skip over this because it doesn't teach you very much. There's a similar formula for L4. So the fourth power of log gamma, nothing about L5 on it. The method of proof simply failed for 5 on. So that's an interesting question. Somebody wants to work in an interesting problem for an integral. I suggest L5 would be a nice challenge.
Victor, are those decimal expansions in the OAIS? Decimal expansions?
Of the L? I do not know. I'm afraid to say.
Oh, they should be.
Yeah. Okay, good. I'll send it to you.
Thank you.
Or I'll put them in.
Or even better, put them in or send them to Robert.
That's what I just said. Yeah, I'll put them in. Yeah. Okay. So then when you play with integrals, you can actually get yourself some interesting problems. For example, you have this number there. That's a real number. You should prove that it's irrational, but that's still not there. We cannot do that yet. Okay. Second problem, you can invent a new function involving elementary functions and the ones you learn, and you have that one. Of course, Riemann beat you to it. And then you can put an integral. You have more collection of functions. You can put an integral, and this game continues forever. So, for example, you can ask to evaluate this integral here. It's some kind of rational function times log of the absolute value of the Riemann zeta function. And you have to prove that it's pi 3 minus gamma over 32.
Mm-hmm.
I suggest that this could be hard because it's equivalent to the Riemann hypothesis. So from my point of view, the Riemann hypothesis is just one integral you need to evaluate. Okay.
So can you do it numerically?
Yeah. People have done this numerically to a gazillion digits.
So you have a numerical proof of the Riemann hypothesis then?
Only up to 1,000 digits.
Yeah, okay.
Okay. Okay, so let me tell you about these brackets. Okay, let me tell you a little bit of these brackets. And so remember that the bracket was this integral here. And A is a real parameter, right? So when you have an expansion of a function, I say a Taylor expansion, for example, with certain coefficients, you can actually integrate term by term. The coefficients are complex. Alpha and beta could be complex also. And then what you see is that the integral of the function f is given by a series of this type. We call this a bracket series. Okay, so every integral comes with a bracket series. So I'm gonna give you some indications about what does one do with this bracket series. First of all, the integrals are divergent, right? So the question is, what is left to do? One can regularize and do something. Then we need to decide rules for evaluating this bracket series. I'll tell you some examples today. Then we need to be able to produce bracket series in an efficient manner. And then the question that Doron doesn't like, what about rigor? Are there rigorous proofs? Well, some people still care, so maybe one should prove something. I have a student who likes rigor, and he's insisting on proving some of these rules. He's doing his thesis, doing more or less, almost all the rules of the method of brackets have now a solid mathematical basis in the old-fashioned way. Okay, here's the first rule. If you ever encounter a sum of R terms in a problem raised to an exponent alpha, what you can do is attach to this sum a certain multidimensional bracket series. Notice that the number of sum, the dimension of the sum is the same as the number of summands that you have there. The formulas involve this function phi that I mentioned before, that is the simple ratio of alternating signs and factorials. Then you raise each of the components of the sum to a power given by a certain index, and then you introduce a bracket. So you get an R-dimensional sum and a single bracket. This essentially is the multinomial theorem. This we can prove. Okay? Second rule. If you get a one-dimensional sum with the corresponding structure, the phi there and the bracket, the way you evaluate this bracket series is by assigning to the sum the following object. You take a 1 over alpha, is the coefficient of the linear term in here. You multiply by gamma minus n star, where n star solves the linear equation. This is what I did at the beginning to solve this integral of the exponential. And then you evaluate whatever is left f at n star. Notice that in order to do this evaluation, one has the function f defined only at the integers. But the solution to the system might not be an integer. So one needs some kind of extrapolation results. And we have some kind of extrapolation results. And actually, one is lucky because Ramanujan did this before us. And this rule was actually invented by this collaborator of mine, Ivan Gonzalez, in his PhD thesis in the physics department in Chile. And he sent it to me, and I sort of tried to understand what he was doing. I realized that this is exactly Ramanujan master theorem. So it's a rule that tells you how to evaluate a bracket, a one bracket and a series. I'll show you examples in a minute. We have a multidimensional version of this rule that says that if you have two brackets and a two-dimensional sum, you get a certain assignment very similar to the one-dimensional. The coefficient alpha gets replaced, obviously, by the determinant of the matrix attached to this problem. And if your determinant happens to be 0, then we don't give a value. So this we can prove. Rule 4 is that if dimension is not square, the system that you get is not a square system, then what you do is you consider separately all the subsystems of maximal rank. And I'll show you an example how it's done. Rule 5 is that if your answer involves a divergent series, then you should discard it. Maybe. We're not so sure about this rule yet.
That's a physics approach.
Okay, divergent series.
That's a physicist's method.
Yeah, they're right. I mean, we should not make fun of them. They are lots of the times are right.
But can you make it format power series? Can you make sense out of it as a format power series?
No, because I want to attach a number. I want to plug in some values in this format power series.
So you want numerics? Yeah. Okay.
I want an answer. Yeah. Right.
Okay.
Okay. Here, let me give you a proof of Wallace's formula. So you write the formula, you write the integral as a power. You know that if you have a power, you can use this rule that says that if you have a sum of two terms to a power, then you can convert it to a two-dimensional bracket sum. There it is, the coefficient, the bracket that come from changing the sign of the exponent and summing indices. You divide by a corresponding gamma factor, and you raise this there. So the integral gets attached one more bracket coming from the integration. When you integrate x to the 2 and 2, you get 2 and 2 plus 1. And so now you have a two-dimensional sum and two brackets. So the philosophy is that one bracket cancels one sum. So once you have same number of brackets by same number of sums, we call it a balance problem, then you get a number at the end. There's your system of two equations, two unknowns that you can solve. There are the solutions. Observe again that, for example, n2 star is no longer an integer. So you have to make sense of this function appearing here at the non-integer values. And there's the rule. You evaluate, and then you need to know something about the gamma function. Well, you can leave the answer as it is there, or you can use elementary properties of the gamma function to get your result. But I want to point out the amount of work that needs to be done to solve this problem, right? If you go back to where I started, after you follow the rules, the amount of work is to solve a 2x2 system with constant coefficients. Here's another example. So you see that not only works for elementary problems. Here's a product of a Bessel function with a trigonometric function. This appears in all these tables. I'm sure Mathematica can do it. The difference is that here I tell you how it's done, not like Mathematica. So there's the power series. You multiply them. Right? This is the integral. And you get a two-dimensional sum M and N are the indices, and one bracket. So this is not a balance problem. You have one series will cancel one of the brackets, and you have a series as an answer. If you choose, this is the case of a non-square matrix that I mentioned before. So this is a 2x1. So you have to look at each of the variables being a free parameter. You choose M to be the free parameter, and the equation gives you N star, and that's the answer. And you can sum this by the binomial theorem, and the condition of convergence appears here. If you choose the other parameter, you get that series with gamma of minus N in the denominator. So everything is 0. So there's the answer, and it's correct. Everything appears, this is what appears in the table, and you can prove it in different ways. Here's a multidimensional example. So you see that one can do all sorts of interesting problems. This is the entry in the table, 4638.3. We apply, you have the denominator, you need to expand because the denominator is a sum of factors. Exactly n factors appear, n plus 1 factors, so you get this n plus 1 dimensional sum, and you apply the rules. Here's the formula you get. The system decouples, so it can be simply solved, and you get the solutions, and there's the answer. Actually, there was an error in the answer in GNR, and we discovered it by doing this problem by this method. There was a typo in one of the gamma factors. It appeared incorrectly. So we have checked, we have gone systematically using this method to evaluate lots of the entries in Nash and Rijik. Okay, let me show you an issue that we have. So these are some famous family of integrals. These are called Ising integrals. There's a multidimensional integral with a rational integrand raised to a power, and the corresponding differentials written in the proper form there. There's a paper, maybe about 15 years ago, by John Borwa and David Bradley, that reduced this problem to a moment of a power of a Bessel K. And Bessel K's Bessel K zeros are not very nice because they have singularities at the origin. So this power series method doesn't work very well. But here's the modified Bessel function. And there are only 4 known values for these integrals, by the way. There's a variety of methods to attack them. The methods have given only 4 known values for when k is equal to 1. And there they are. First one is 2, next one is 1. For the third one, you get an L series. And for the fourth one, you get zeta 3 times a rational number. And that's it. So we thought this method of brackets is ideal to attack this kind of problem. And I will show you our attempts. It is sad to report that the only ones we can evaluate are these 4. we can confirm the 4, but the 5th one is a challenge. But I'm hopeful. Eventually I'm going to have an optimistic graduate student that will evaluate C5. We'll see.
So is your proof better than the one Borwan et al. Had?
Well, the proof simply reduces the integral to a very small system of equations.
So this is the value of C sub 4 is due to you or to?
No. These are well known for about 15 years.
So you have a new proof.
We confirm these 4 values with the method of brackets. Yeah.
Okay, that's nice.
But the amount of work is minimal.
And Victor, again, please make sure these constants, the decimal expansions, are in the OEIS.
Okay, I will. So here, let me show you how we do it. Here's C21, is this double integral. So you apply the rules. There they are. So you expand this rational denominator appearing here, their integrand. You expand following the method that says you have 4 terms here. So you get a 4-dimensional sum. So the first step is no thinking. You take the integrand, you see a sum of 4 terms, and you apply the rule. You get a 4-dimensional sum. And you get that. 3 brackets and 4 indices. So you expect that the answer will be a 1-dimensional sum. Okay, so you get 4 inside 3 brackets, 1 free variable. Okay, so what happens is this. You take n1 to be free, and then you get this, right? You get for the answer for the integral I2, you get a divergent series because you get the gamma of minus n1 appearing in this as a summand, in the summand, right? So it's divergent, the method gives no information. Okay, but look, this is a problem that we started by simply expanding the integrand without any manipulation. So I thought, okay, maybe what I should do is manipulate the integrand a little bit. By the way, in this way of doing it, if you try the other 4 indices as free, you also get divergent integrals. So what should one try to do next? Okay, I take the integrand and I multiply by x times y, so I get this form here. I do it again. I have 4 terms in my sum, 4 summands. I get a 4-dimensional series, and then every one again gives me divergent integrals. Well, maybe it's time to give up. Here's another idea. I take the integrand, this polynomial in 2 variables that appear here, and I'm manipulating this form. So x times y, x plus y, and x plus y. And then what I think of this is 3 terms now. There are 3 terms in the sum. I used the usual methods. I get a 3-dimensional series now, and I expand. Doesn't work. And then what I do is I couple x and y and treat it as a single term. So now I have 2 terms. I get a 2-dimensional sum, right? And then you get I2 equal 1/2. So the problem that I have is that as of now, there's no methodology. There's no way to decide if you have an integrand that has a certain combination of terms. We do not know how to couple them, how to put them in groups so as to make the method work. I think it's an interesting formula. We have other interesting project. We have other examples of this type that, because we simply don't know, right? As of now, it's brute force, and this we try until something worked.
This is like one of the Hilbert problems. You're trying to reduce the number of variables.
Oh, I don't know. Okay. Yeah. But I'm trying to that's exactly what I'm trying to do, and trying to do it in such a way that I don't get a divergent integral at the end in this procedure, in this bracket procedure.
I guess Hilbert would say, is this a genuinely 2-dimensional? Is this really a function of 2 variables or 3 variables, and you're looking for new variables?
Then yeah, okay. So so I hope that I made my point clear that when I have this long explanation, there are many ways in which to couple these terms, and I don't know which is the most efficient. There has to be a rule. There has to be a rule hidden somewhere in here.
But you can try all the possibilities. There are finitely many of them, and try them out.
Yeah. But that's not what I like to do, Doran. I mean, there has to be a reason why one of them works. There has to be a reason behind this why certain one work. I grant you.
So
if you have a small problem, huh?
So why don't you factorize x plus y out in the denominator?
Yeah, because then I have a sum of 2 terms, and then there is a much more complicated problem to do with brackets.
Okay.
Yeah. So it's not clear to me how to make the manipulation of the integrand before I apply the method of brackets. I don't know how to do that in an efficient way that will help me solve the problems. Okay, so the type of problems that originally the method was applied to was, and this is the origin in which Ivan started working on, is in the calculation of certain Feynman diagrams. Okay, so here's an example of the Feynman diagram. Think of it as a graph, right? you have a array, you have incoming variable, incoming rays. So they get a point where they split. Maybe this corresponds to physically a particle that gets cut into two particles that move. And then there are places where they get reunited. And each diagram has two types of rays, two types of segments, the semi-infinite one, for example, like one coming from P2, P1, and P3. And then there are these finite rays that come from the internal structure of the diagram, right, that connect two vertices. So Feynman's idea was to represent all the physics having to do with the particle interaction by these diagrams. And there are rules that tell you how to compute certain physical objects from certain analytic objects attached to the diagram. One of them is something called the Schwinger parametrization, that essentially what you do is you use the variables inside the loops, inside the finite loops, and you produce there's a rule that tells you what kind of objects you attach, and Schwinger gives to this diagram, to each internal loops, it attaches a certain integral, and this is the example that we get here. Okay, all these rules here are specific. So what I'm trying to point out, that from my point of view, what you see is that a Feynman diagram produces a multidimensional integral. Some of them are very hard to compute. And the origin of the method of brackets was to actually try to do something with them. Okay, so you see you have this rational exponents. D is the dimension. For example, so in physics, the dimension is usually 4, but it has to be some kind of regularization attached to the problem. So usually it's 4 minus epsilon, because otherwise the integrals diverge. But we don't worry about that now. Think of D as a parameter. The m's appearing here corresponds to the masses of the particles, and the p's are momenta. So there are certain coefficients. The coefficients appearing here come from Schwinger's rule, and they're polynomials in the variables that you're integrating respect to. So this is a simple diagram, and it produces this monstrosity as the integral. So I want to walk you through what the brackets does. And so conservation of momentum, remember that the diagram is like this. Sorry, the diagram is like this. So you apply conservation of momentum. The incoming momentum is P2. The outgoing is P1 plus P3. So conservation of momentum gives you a relation between these variables in the integral that you have to use. And that's the integral we to compute. Again, it's a three-dimensional version with some exponential with a natural quadratic form, and then this exponential with a more complicated object here. And the question is to evaluate this integral in terms of the parameters. And I'm going to show you the example, the simple example where all the masses are 0 and all the momenta square are 0. So you get an integral like this. It simplifies a little bit, not much. And so then what I do is I look at the sum appearing here. The sum of 3 terms produces a three-dimensional sum, and the expansion of the exponential produces one more dimension, one more series. Right? You notice is if you expand the exponential, you get the term x1 plus x2 plus x3 again, so you can couple it with this one. So the way you expand these things has to be done in the right order to get simple expressions. And you get this 4-dimensional problem. And what you notice is that the deltas are these 4 brackets. So the deltas appear here, right? So now you count. And what you have is a 4-dimensional sum and 4 brackets. So the rule is that each sum counts as a bracket. So this should give me a number. This is a balanced problem. Okay? So then I have there are the brackets. Now I have 4 brackets. So the problem involves to solve a 4x4 system. That I can do even by hand. And at the end of the day, the problem has no free indices. So I get the solutions there. And that's it, right? So I remember we tried to compare, there are these papers where appear these calculations that they are interminably long. I mean, there's papers to evaluate these Feynman diagrams, some of them are quite long. And so this is very efficient somehow, this method. Okay. Okay, so I think I spoke too fast, but I was very afraid that my battery was going to die. So I apologize for finishing earlier. One of the best advice that I got as a graduate student at the end of my graduate school, my advisor told me, do never go overtime. Nobody's that interested in what you have to say. So at least. So one thing that I want to finish by saying is that we have used this method to evaluate a large collection of integrals. I mean, we have evaluated, I don't have an accounting of this, but large number of the integrals appear in rational-Riesic. We have evaluated. We have papers that people send us, and we try to use the method of brackets. Every time the method gives you an answer, it gives me the correct answer. And by the correct answer, what I mean is either I have an analytic expression for the integral, or I have a numerical expression. So when the method succeeds in giving me a number, then if I have an analytic expression to compare it with, then I'm happy. If not, what I do is I do a numerical evaluation of both cases, and so far we have not found one example where the method gives me the incorrect answer. So that's hopeful. Okay, thanks for your attention, and sorry that I spoke too fast, but I had this big fear of technology that my battery was going to die. So
Thank you for going under time. So you have plenty of time for questions. In particular, being a mathematician, I have a question. Isn't it a tautology that everything you do is correct?
sorry?
You said that everything you do is correct. How could it not be correct if your method is a valid method?
No, what I'm saying is this. What I'm saying is that if you evaluate an integral by the method of brackets, right? Correct maybe is the wrong word, but
in other words, it's not rigorous. That's what you mean.
No, what I mean is this. If I have an integral that have an integral equal analytic expression, and I use the method of brackets, it gives me the analytic, if it works, it gives me the analytic expression that the person gave me.
Yeah.
If I don't have an analytic expression for the integral, the method gives me, if it works, it gives me an analytic expression, sometimes written as a multidimensional series that I cannot simplify. But numerically, I can test the original integral doing numerical integration, and I can test numerically the answer that I get, and I get a correct answer to a satisfactory number of digits.
Oh, so there's a check for the validity of the method, even if you don't have a closed form. Yeah.
Correct.
That's very nice.
Correct.
Yeah.
Yeah. So of course, this method applies only to integrals from 0 to infinity. One can transform every other integral, but in many senses, it gives sometimes the integrals become much more complicated, but so far it works.
Is it beautiful?
Yeah. So as of now,
I mean,
we're at the point where most of the rules now are being proven by the student of mine that insists on proving them. So it's not so much a heuristic method anymore, but I prefer the heuristics because it's easy to operate. So it reduces the problem of integration to a problem of solving a linear system, usually of small size.
That's very nice. Is it implemented by a computer, or it's everything is by hand?
Yes, we have a Mathematica package that is not to be shared yet because Karin Cole is doing it, and so we're trying to debug it and make sure that.
Very nice, very nice.
Yeah.
Questions? Other questions for Victor? We have plenty of time.
Yeah, me.
Okay, go ahead, Michael.
Yeah, okay, Victor, very nice talk. I have a question regarding the speed of the evaluation, assuming, say, you get all the Feynman diagrams that you evaluate that they would come out right. And of course, the point is that there's a very convincing argument, also not rigorous, but a very convincing argument by Freeman Dyson way back that even after renormalization of the perturbative series, right? So then you cannot sum it up. So it's it won't converge. Now the physicists are lucky in some sense that they are only able to compute, say, half a dozen terms, thanks to supercomputers, and then they sum it up, and the numbers come out usually quite neat. Now, at the same time, if it would be easy to sum up, let's say 137 terms, or actually 137 should be optimal according to Dyson, because of 1 over alpha, right? So let's say if with ease you could sum up 200 terms, right? You should suddenly get a bigger discrepancies, right? And so then, of course, physicists would be hard pressed to say why they stop with 7 terms if it's easy to compute more. Right now, they cannot compute more. So what is your take on this? Do you think you can push the method to actually get beyond 137?
Okay, so I had a student who finished a thesis last year. And first of all, every time we submit a paper with one of these methods, the referees usually says, this is dimension regularization. This method is nothing but dimension regularization. So she made a very strong convincing argument that this is not. So she took lots of examples in the literature and solved them by different problems. She computed amount of work required and the type of things that were being done. And so the method of brackets, even at the heuristic level, is not just this dimensional regularization. Right. So first thing, and then she compared several calculations with Feynman diagrams, and she evaluated. She was most interested in the ones that would produce closed analytic expressions. So this is the kind of thing she was doing. But it's there. The method is there. Sometimes with Feynman diagrams, with multi-loops, for example, the problem becomes increasingly too large. So it requires our mathematical code to be implemented in a nice way, and that's what we try to do now.
Okay.
But they reduce, but the problems get reduced. So the string of parameterization, they get reduced to integrals of the method of bracket gives sufficiently small size systems of equations. So the amount of work that is done is minimal. That's the point that we try to convince people to do. Yeah.
Okay. Yeah, thank you. That sounds really very interesting. So I'm curious what will come in the future.
Okay, good. I'll keep you posted.
There are more questions to Victor, but I have a general question. Is there a new edition of this integral table of graphs that you are editing? Is that true? Or
Yes, I am the so-called scientific editor. So I'm in charge of checking. We're coming with a new printed version within 6 months, more or less.
I see.
And there are no more typos. You get rid of what? And all the typos you found are corrected.
Well, all the typos that I found are correct. That's correct statement.
Is there a list of typos for the various versions?
Yes. I think it's online. There's some early papers in math communication, math computation, math comp. There used to be papers in which people will publish the list, but we keep. There is an electronic version of the errata that we have. So compared to the latest edition. So
I can find it on your website, or
no, but I can find it and email it to you. So I should put it on my website, really.
Okay. Thank you.
The thing that has not been done properly, I think, the thing that we need to do for this table is the real check on the validity of the parameters of the problem. I mean, the range of parameters for which the integrals are valid. And there are errors of the type that some integrals were copied from one place to another, and they switch alphas and betas, and so the ranges were wrong. So there are all sorts of things like that. And my impression, this is purely anecdotal, but I think that Mathematica today can do about a quarter of the integrals that appear in Gaussian heuristic.
Oh, not bad.
Yeah, no more. Right? Yeah.
Victor, how about a new edition of irresistible integrals? Seems like maybe you could use a chapter on the bracket method.
No, I think it's that was a labor of love with my former student George Boros. But maybe there's a volume 2. There's a volume 2 that has been in preparation forever. So maybe brackets will be in there.
Oh, I can't wait to hear about it.
Yeah, it'd be nice.
Yeah.
So, more questions for Victor? Well, thanks for a great talk, and see you
Okay,
next
thank you
week.
for inviting me. Thank you for.
And-
Hopefully, one day we'll see each other in person. But
Good, and keep up
Yep.
the good work with the integrals. So, wow, it's really good. Perfect. Thank you.
Bye, everyone.
Bye bye.
okay, bye,
Bye-bye,
everyone. Good to
Bill.
see you. Good to see people, even though it's on the screen.
Thank you.
All right, bye everyone. See you back next week.
Thank
Bye.
you.